Hello, friend. My name is Derek Carter, and in this video, we're going to start our journey looking at operating systems. So this first one is we're using the xv6. So xv6 is a simple Unix-like teaching operating system. I'll talk a lot more about it, but really these videos in this operating system course is using this actual working small version re-implementation of Unix version 6 in order to discuss and understand the properties of operating systems, how they work, things like that. So in this video, we're just getting started. So there's a little bit of some general stuff about, what makes an operating system, what it does, and then we begin looking at, in particular in this video, we're going to look at the system call interface for xv6. So the small set of system calls that are implemented that were derived from, inspired from the version 6 Unix that this operating system comes from. And also we're going to talk a little bit about processes and memory. So one of the most important abstractions of an operating system are processes and how those are implemented. So if you're ready, let's go ahead and get started then. So to begin with, the purpose of an operating system, its job is to share a computer among multiple programs, and it provides a more useful set of services than the hardware alone supports. Okay, so operating system sits on a level between the hardware and user programs or user applications. So working directly with the hardware, there's lots of details. It's very difficult. So one of the purposes or jobs of an operating system is to provide high-level abstractions for the low-level hardware to make it easier and much faster for people to write applications to use hardware like disks and keyboards and video displays and things like that. So one way you can think of an operating system is as a resource manager. So a typical computing system has lots of resources like memory, files on a hard drive, other devices and things that need to be shared among multiple programs. So fundamentally, modern operating systems are multi-process systems. They allow multiple applications to be running in parallel, and they need to have a way to share and manage those resources. And that's one of the primary responsibilities of the operating system. Operating systems usually provide mechanisms to allow programs to interact, either indirectly or directly. So especially on a modern hardware architecture that has multiple CPUs or multiple cores on a single CPU chip, we can often parallelize solutions to problems, so allow the program to run on all of the cores or all the CPUs that are available, and thereby solve a problem much faster than we could do if we don't have any sort of parallelism. So if you've never thought about it, or thought about what an operating system does, what it is really doing is providing services through an interface, the what we call the system call API or application programming interface. So the version 6 Unix is, there's an argument to be made that kind of all modern operating systems, including Windows, but Unix variants, Mac OS and things, POSIX, Linux especially, all kind of derive the basic ideas from these versions of Unix. So the most kind of successful system call API all derived from this, and I'll go into this a little bit later on in this video. So there's lots of reasons, discussions people have made about why the Unix system call API was so successful. It's simple and narrow and easy to use, so it provides basic mechanisms. So the system calls provide basic mechanisms, but they're powerful. They can be easily combined generally. Okay, so this is often kind of thought of as the Unix way of providing services, small things that can be combined generally to create complex solutions to things. So just a little bit about the operating system code that we're using in this class to study and modify and learn about how operating systems work. So we're using xv6, which is kind of a re-inspiration or kind of inspired by the version 6 Unix. So my understanding is that pretty much, I mean, you know, it doesn't have any source code, so it's a re-implementation, and it pretty much implements the full system call API, maybe not 100%, but a lot of that API call that had been defined in what was called version 6 of Unix. We're using a RISC-V port of this, so I think they originally did xv6 in x86. So, you know, RISC-V is an interesting hardware architecture. This isn't really a computer architecture course, but when we're looking at the code, you will have to look a little bit at RISC-V assembly and understand some basics, but it's pretty easy to understand RISC-V assembly, so you'll get a little bit of that. I wanted to kind of pop up this history of Unix just real quickly. So this is just the Wikipedia article for Unix here. So, I mean, Unix was mostly Ken Thompson and Dennis Ritchie. And I also think of Brian Kernighan. I think he's mostly thought of as kind of the guy who wrote C that Unix was written in. So I'm sure this history of it kind of talks about that. I don't remember which version where they kind of had the C language of Unix and started rewriting Unix in C. Basically, version 6 from Bell Labs comes in here in like the late 70s. Which is what our code is based on. But really, I mean, all of these, so the standards, nowadays we would probably call this the POSIX Unix standard. I mean, most all of these, like Linux, the BSD, the Mac OS, the Mac OS comes from, and all these System 5 stuff over here, kind of use these POSIX standards, and you know, these evolved really from like the System 5 Bell Labs version of Unix. You can read that history article if you want more details. It's an interesting history, but you know, and so the modern POSIX is much more complex. But you will, you know, if you study this teaching operating system version of re-implementation of version 6, you will see the bones of kind of the modern POSIX. So most of the stuff is there. They just there's more system calls in the API and more detailed kinds of things. So this is just a simple but a classic view of kind of the split of how an operating system works. So the operating system is really the kernel. Another name for the operating system is the kernel. It's a special program that provides services to running programs. Okay, so we define a set of system calls, which are really just function calls, which is the API. But we're going to talk about kernels and processes in this video. So a process is just a running program that uses the OS kernel services. So a process consists of allocated memory that contains constructions and allocated memory that has data for those instructions to perform computations on. And there's other structures. So there's like a process stack or a function call stack. There's going to be a system stack that's part of that's owned by the kernel. And in general, the hardware has to support a split between a kernel mode and a user mode. So the kernel mode, probably jumping ahead here a little bit, but the kernel mode has, the user mode is the less privileged mode. So certain instructions and certain things can only be done in kernel mode. So things like setting up memory and implementing virtual memory and other stuff. And you'll see kind of details of what that is. So you first, in order to call a system call, you first have to switch the mode at the hardware level into kernel mode, and only then are you running in kernel space, and then you can run the privileged instructions to use devices, to manage memory, and things like that. So when a process needs to invoke a kernel service, it does a system call. So system calls are the calls in the operating system's interface. Okay? So, and yeah, I already mentioned probably all these things. So, you know, the kernel space is the privileged mode. It has to be supported by hardware. So modern operating systems require that the hardware architecture have at least a more privileged and a less privileged mode, and that more privileged mode is the only, you have to be in that more privileged mode in order to do certain things. To set up virtual memory, set up memory paging and page tables, and other things that you'll see examples of lots of other things by reading the xv6 code. So we split that between kernel space and user space. So normal programs are going to run in user space. Whenever they need to do something that is the purview of the operating system, they have to call one of the operating system call APIs in order to have the operating system do things, like create files or allocate more memory or stuff like that. So this is the complete set. I believe this is the complete set of system calls for the xv6 teaching operating system that we're going to be studying and modifying in this course. So there's only 20 or so here, but again, if you go on and look at like a modern POSIX Unix-like operating system, you'll see that there's many more system calls in a modern system, but these kind of provide the bones of what we would think of as a modern Unix-like system. So everything from fork to exec here, we're going to kind of cover in this video. So these are really the API for creating processes, for having a process execute, load and execute a different executable. I'll talk about these here. There's a split between creating a process and then actually executing different code or different instructions. Another thing, so when the process is done, it needs to call exit, a process can wait on its child process. So really, these are all part of the kind of creating processes and manage processes. The only one that's really kind of memory management is the SBRK here, which is how a process requests new memory so that the operating system can allocate new virtual memory pages using sbreak. So things from open to pipe here are part of the file descriptor interface. So files can be attached to an actual file on a hard drive, but these are really kind of a general way of defining a byte stream and passing streams of bytes back and forth between sources, which might be files, they might be buffers, they might be devices, things like that. Okay. And then finally, change directory, make directory, and things like that will be in the third video for this first chapter here. Those are the actual file system kinds of things for how you define a hierarchical file system, and you create directories create files in the directories and things like that. So a process in general on almost any operating system, but in xv6 as well, consists of some memory allocated in user space that holds the non-privileged instructions and data and holds a non-privileged stack usually, so the function call stack. And there also might be like a heap for dynamic memory allocation, deallocation to hold data that dynamically might be created by the process. And then there's also some privileged parts associated with every process that are owned by the kernel. So xv6 process, each process is going to have a per process state that's private to the kernel. So this is part of the process table that's implemented and maintained and managed by the kernel in order to manage all the processes that are running simultaneously. So as we'll see here, the kernel associates what's known as a process identifier, or PID for short, with each process. So each time you call fork, a new process identifier is assigned to the new process that's created by that fork system call. So xv6 is a time-sharing system, a time-shares process. So even if there's only a single CPU, you get the illusion of parallelism because it rapidly will switch between all the current running processes and give them a little bit of time, and then switch to another one and give it a little bit of time. We are using the qemu emulator, which can actually emulate to multiple CPUs. So when you have more than one CPU, xv6 still works. It will transparently switch between the available CPUs among the set of processes that are waiting to execute. So in this class, we can actually simulate a true multi-CPU system, so have true parallelism. xv6 doesn't actually implement what are known as threads. We'll probably talk more about that in this class here. So there isn't threading within a process, but you do get parallelism by having multiple processes that are you're either time sharing or the multiple processes are truly running in parallel if you have more than one CPU available on the hardware. So looking at the system calls that deal with the process abstraction in the xv6 operating system, a process can create a new process by calling the fork system call. Okay, and this is still pretty much the same in modern POSIX systems, Unix-like POSIX-based systems. Just to create a new process, there's a single system call fork. So fork actually returns twice. So whenever you call fork, a new process is created, so it actually the operating system allocates some new memory for that new process, and it makes a copy of the calling process memory into the new one. So for xv6, we'll talk some more details about this later on, but for xv6, it just makes an exact copy of the memory, of the code and data of the running process for the new process. For the allocated memory that's allocated for the new process. So it actually returns twice. It returns with a return value of 0 in the child, okay, and it returns a non-zero. It actually returns the process identifier of the new process that was created back in the parent process. If I forgot to mention or emphasize that for most of these system calls, they actually return an integer value except for the SBRK. So in general, 0 indicates an error, and -1, 0 indicates a successful return, a successful call to the system call, that it worked correctly. And a non-zero value usually means some sort of an error occurred. So the xv6 returns -1 pretty much consistently to indicate an error. But a fork is a little bit different. So a fork returns 0 in the child, which means that the child was successfully created, but the parent does expect a non-zero return value in this case. That's still a successful indication, but in the parent is going to receive the process identifier that indicates that the child process was successfully created. Every process should call exit. If you don't call exit, it will normally be done for you. If you go to the end of like your main function and don't call exit. But to be safe, you should always call exit. This causes the process to stop executing, which is the signal to the operating system to release the resources back to the kernel, such as memory, open files, and other resources. Wait, we'll see an example of using wait here. A parent can call this on the process identifier in order to check whether the child is exited or not. And then there's a way to get back. So when you call exit, you can return back a status code, what's known as an exit status code. And by convention, you usually exit with a value of 0 to indicate I succeeded. There was no errors, or a non-zero exit. And then the parent can receive back that exit status code if it needs to. Although you'll see in our example here, we don't actually receive back that exit status code. We just ignore it. But we do call wait to check whether the child is still running or to figure out when it's exited. And then the fork doesn't actually load new instructions. So it's just a copy of the instructions and data of the parent process and the child process when you call fork. There's reasons why that happens that we'll talk about, and that can be advantageous. So, for example, the open file descriptors are actually copied initially, and that fact is used by lots of processes. But so if you want to actually execute a new set of code, you have to call an exec after a fork. So a common pattern in the child, if we return back and we see that 0 was returned, indicating where the child process is, we'll call exec to load a new set of instructions and data from a file and start executing those instructions. Okay, so for the rest of this video, I'm going to show an example of the system calls we were just discussing. So we'll start with an example of fork, although this also demonstrates fork, wait, and exit system calls here. I'm going to show these examples in a running XV system being emulated on the qemu emulator. So there should be more information in this course in the getting started section and the getting started video. So if you don't have your environment set up so that you can actually run compile and run qemu, you'll see me doing this here, but you might need to do some other things to get your environment cloned and set up so you can do this stuff. So let's show this example here. So let's look at those examples. So I mean, I'm using our a clone of our repository, which is the class resources repository. If you don't have this set up, you should go back and look at the getting started video to get everything set up. So I'm running in VS Code here instead of a Docker dev container. I've already done the things in order to create a subdirectory in this container called xv6. And then all the code is actually in the xv6-risv here. I should be able to change into that directory if I want to compile and run these code examples. Like is shown here in this README, there's some stuff you have to do before you can get to this point, but you should check. You should be able to in your environment, you need to have a version of the RISC-V compiler, so that command should work. It might not be exactly the same version. You also need to have the qemu emulator system installed, so that should be available there. To do these examples, yeah, I mean, if you want to compile and run the emulator, you just do a make qemu from this location here. But to do these examples, I've got in our class repository, these won't all be in there to begin with. So we're working on this example 1 and 2. But in order to compile these and try these out, I need to copy these and we need to paste these into the xv6 code directory so that when we build it, it'll actually build these. So these files are actually user programs. So I'm going to actually just paste these into my xv6 RISC user subdirectory here. Right? So that put example 1 fork and example 2 exec in here. But we also need to modify the make file to include these in the build before we build these into our running version of xv6. So if we open up the make file, inside of the make file, if you scroll down in here, you'll see an objects, but you should see a user program. So basically, you have to follow the same format here. It needs to be underscore, but like ex1 dash, what were the names of the programs? I forgot already. So example 1 fork, without the .c, they need to spell them correctly or else you'll have problems. And then example 2 exec, like that, right? So it needs to have the underscore, but it needs to be the same name otherwise, except for the underscore in front, and you don't have the .c or any extension. So once you've added those to the make files, we have the files in your user subdirectory from where you're building from. We should be able to do that make qemu. This will build everything in the user, all these user programs will get rebuilt if they need to, and then we'll start up the qemu emulator. Okay? If you get an error there, then there might be a problem, but it should actually boot up into, we're actually running the xv6. Okay? So let me open up the example 1 fork, so we'll get back to what we want to actually do. We want to actually look at this example here. So when I compiled and ran this, if you do an ls to do a directory listing, you should see there's lots of user programs in my current working directory, including ex1 fork and ex2 exec. So if you don't see those, you didn't correctly get them built, the user programs built and available here in your home directory when you start running. So back to our first example here. So the fork system call is called here. Remember, this returns twice, right? So in the parent, it's going to return with the process identifier of the process. So what happens for the parent is this will be greater than 0. So this code will get executed. Remember, when we do a fork, all this code is copied. So the same code that gets compiled here and is being executed is copied in the parent and child, but after the fork returns, there is a difference. So the PID will be non-zero in the parent, and we will just display what the process identifier was for the child, and then we call wait, okay? So as I mentioned, if you need to know what the exit status code is that the child returns on exit, you can actually pass in a pointer here. But we're just ignoring whatever the exit status was for our child. But this will cause the parent to wait. If there's no child processes, wait will return immediately with like a -1, I think. So that's kind of an error. If there's more than one child process, wait will, whatever the first child exits, wait will wait until the first child exits and then will return. So you have to actually have a loop if you're expecting multiple children to be forked, and you need to wait for all of them to finish before the parent finishes. So that's basically the parent here. So it basically prints out. This was the identifier of the child. It waits for the child exits, and then after it's done, it prints out this message. Now the child receives a 0 from the fork. Right, so if the process identifier is 0, this code will be copied over and run on the child. I forgot to mention, so if you don't have a pause in here, I wanted to show what that looks like with the pause. I'm gonna comment that out and recompile this. So when you're running in the emulator, if you do Control A and then a question mark, you can actually access the emulator things in order to send a break or do other stuff. So if you need to exit the emulator, you want to do a Control AX to exit the emulator. So I'll do Control AX to exit the emulator. I'm going to recompile so I can recompile it with that commented out there. All right. So in the child, back to this, in the child, all it does is it just exits, right? So it just prints out a message and it exits. So this calls the exit system call, which the parent should be waiting on. And again, if we needed to know what that exit system call was, we could have passed in a pointer here and got the exit system call, the exit status code here. And by convention, we usually exit with a 0 to mean everything was okay, and a non-zero value is usually given to the exit system call to indicate some sort of an error or problem, so we can communicate that back to the parent process if needed. And let's try running that. So again, if you do an ls, you should see there's user programs that can run, including, you should see the x1 fork and the x2 exec if you correctly copied these over and built these, added the lines in your makefile so that we actually built these user programs here. So if I run it, you'll notice that basically the parent and the child, this is part of the time sharing. So the operating system is switching back and forth between these. So before the parent message completely got printed out, it actually switched over and started executing the child here. So it's a little bit tough to see the two messages here. Right. So in modern POSIX systems, it does some stuff to not have the buffers if they're both outputting to the same standard output. But for us, if we want to more clearly see this, we might want to add the pause here. This is another system call that I didn't mention, but user process called pause to have it pause for. This is actually, there isn't, I don't know if this was actually part of the original Unix System 6 or not. There's a sleep call in modern POSIX systems which does a similar thing, but sleeps for a number of seconds. Pause just pauses for a number of clock ticks, is what's happening here. So I'm going to actually exit here, Control AX, exit, rebuild. and try it again. So with the pause, you notice there's a little bit of a pause and we get cleaner output. So, the parent immediately outputs. So in this case, the child was assigned to process identifier 4, and then the parent ends up waiting at this point before it does the next printf. And the next thing we see on the output here is that the child, after pausing for a bit, exits. And then that allows the wait to return here, and back to the parent, it prints out that the child was done. So let's look at the second example program here. So it has the same structure. It's just that the parent does exactly the same thing as we did before. So the only additional thing is we give an example of the exec system call. So if you want to actually run a different set of instructions and load a different set of data, you have to do a fork followed by an exec. So this is a common pattern, this fork exec. In modern POSIX systems, there's no longer just a single exec system call. So here's where we're calling exec. There's kind of like a family. There are different ways to invoke exec to load. But what is being done here is we pass in the name of a program. So this expects a program to be compiled, here it should be in our current directory, whatever our current directory is when we call this program. So there should be an echo program here, which is already compiled. It should be in ELF binary format. So we'll talk more about kind of the format for binary files for code in our system here. So it takes the name of the executable. That is what's going to be reloaded into the memory that's allocated for the child process, overriding the code that was compiled and the parent is running. So the basic idea for exec is we actually pass in what are known as arguments or command line arguments. We'll talk more about these later on, but conventionally, the first argument is going to go in what's known as argv, arg value 0, which is always just the name of the program. So, if I'm running echo from the command line just by hand, I can provide several command line arguments. So command line argument is always going to be the name of the program, how it was invoked. You have to do the same thing if you use exec, but I can pass in a command line argument 1, 2, 3, and 4 here, and it will echo these out in the echo program. That's all echo does. So this will do the same thing. It should just echo hello when we exec. After doing a forking exec on the child, we should just see hello echoed out. So, this might be confusing if you do this. So basically, if you give a command that's not an actual valid name of a process that's been compiled here, of a file that's been compiled here, you'll get an error from exec, or at least that's what our shell is given here. So just be aware of that. But what's happening here is you had a typo. So the actual name is exec, not fork. So again, and we have the pause in there. So in order to avoid that garbled output from them both sharing the same standard output here. But now, so we ended up with process identifier 10 now for the child, and this hello here came from actually the exec here. Right? So by calling exec with these arguments, we ended up calling exec as if I had done it like this from my shell here. So, sorry, as if I had done like this from my shell here. Did an echo and passed in just one command line argument of hello. So that's why we got the hello on the output here from calling the exec here. Okay, so with that, that's it for this first video, the first part of chapter 1. So in this video, we start off with just some general things about operating systems. So, what they are. You can think of them as resource managers. It basically is providing a simplified API between user applications or user processes and low-level hardware. So basically, they are managers that allocate resources to share among multiple programs. So they share and manage processes, share resources, manage resources to allow multiple processes to run and use the hardware successfully. And then we specifically looked at our xv6 teaching operating system calls, specifically the system calls that deal with the process abstraction. So so fork and exec and wait and exit being some of the main ones that provide a process abstraction and a way to create processes and run new sets of instructions and code on the system. So, you should kind of be aware of what we mean by the kernel and the kernel space. Kernel provides a set of services, provides the system call API. Kernel space is the more privileged mode supported, and we need certain hardware mechanisms in order to differentiate between a more privileged mode and a less privileged mode so the kernel can use and implement these kinds of things. And processes is the first sort of abstraction that we talked about that operating systems provide. So modern operating systems all have a concept of a process. So a process is a running program that uses OS kernel services, and processes run in a less privileged mode. So a normal unprivileged mode called user space or user mode. All right, so that's it for this video. Let me know if you have questions. Let me know if you have any feedback or ways we can improve these videos or this class. Otherwise, I hope to see you in class or hope to see you in the next video.